In this next unit, we're going to be looking just for a brief time on Chapter 13, a little bit about alcohols, phenols, ethers, thiols, and sulfides. All similar functional groups in that they have tetrahedral geometry, they're single bonded all around, but these will lead into our focus on Chapter 14 and chirality, very important topic in organic chemistry. Clearly, you want to be able to recognize the functional groups: alcohol, phenol, this is review, ether, thiol, sulfide. So they all contain oxygen or sulfur, which is right below it in the periodic table. Other than phenol, actually, they're all tetrahedral and single bonded all around. So phenol doesn't fall into that category. You can go through the beginning parts of this chapter. I haven't assigned very many practice problems because it's really not necessary to know how to name everything under the sun. But you can get the idea of the simple naming of some of these. For example, the alcohol right here would be 1, 2, 3, 4. That's a butane. But since it's got an alcohol at 2, it's 2-butanol. So you get the idea already. That's the kind of naming of alcohols. You can remember that there's primary, secondary, and tertiary alcohols. We already went through naming of phenols. Like, for example, if I put a chlorine there, it's 2-chlorophenol, 1, 2, and so forth. So the most important part, other than the chirality at the end, is this reaction of alcohols, which is the reverse of hydration. It's dehydration. If hydration was the addition of H2O across a double bond in the last unit, dehydration is the loss of H2O to create a double bond. So it's the exact reverse reaction. You can draw in implied hydrogens to make clarity if you want. But basically we're going to eliminate a hydrogen from one carbon and the OH from from the neighboring carbon to create this alkene right there. And it's done under acid conditions. If we do the same here, if we draw in implied hydrogens, we are now reversing colors. We're eliminating H2O from the molecule to create an alkene. And remember, there is still the 2 hydrogens there. So the 2 other hydrogens are still there. You've lost water, however, and the electrons involved in the covalent bonds to OH and H on the left end up here. If anyone is interested, you can look at the reaction mechanism for that. It's actually pretty interesting. Or you can ask me. So we already covered, in fact, also the reactions of alcohols and phenols with base. So the above elimination was with acid. Actually, the elimination can occur with base as well. I'll mention that as a side. What I already showed was that NaOH exists as a salt like this, basically. The OH is a Lewis base. It can form a new bond by donating electrons to that proton, displacing these electrons onto the oxygen, and the oxygen then has extra negative charge and is negative. The same thing basically can happen with the OH group of a phenol. Exact same reaction leading to this. The book points out that this probably does end up pairing up in each case with a sodium counter ion, I guess we would call it. So it makes these are sort of like salt-like structures. Remember, salt is sodium chloride. Well, plus minus sodium chloride, plus minus sodium, whatever this is. Okay, we can skim over a lot of that. Remember the dehydration reaction, especially. As I said, this topic segues into the topic of chirality and stereochemistry. And that's because all of these kinds of molecules with groups like these, alcohols, sulfides, thiols, etc., have a something that looks like this. In other words, this could be O or S. This H here could be a carbon group, and then it would be an ether. But essentially, you end up with something that can draw your attention like this, where this carbon that the alcohol is attached to has 4 different groups attached to it. What are the 4 different groups? A hydrogen, alcohol, 1 carbon chain, and then a slightly shorter carbon chain. With respect to that carbon, there's 4 different things on it. What has been discovered, is that if you switch any 2 of those groups, in other words, if you detach any 2 of them, like if I detach this group, and then switch them and reattach them, I create a different molecule. And this is not a new concept. We saw it with isomers earlier on, and that's exactly what's going on here, except for different terminologies. These are isomers. So if you look below, the switched version is here, the original version is here. They are not the same. You cannot take those 2 molecules and superimpose them. If you built molecular models of them, which I'd recommend having a set, there's no way you could turn them around or twist or do anything from the left to the right and make them the same. They're not the same molecules, and therefore they need different names. And how to name them is a little tricky, but also pretty fun. And so that's actually what we're going to spend a lot of time on this week and in coming weeks.